Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on chemical kinetics. Let's go ahead and get started with problem number 1. Problem number 1 says in a third order reaction involving two reactants and two products, doubling the concentration of the first reactant causes the rate to increase by a factor of 2. What will happen to the rate of this reaction if the concentration of the second reactant is cut in half? So let's just set up a very general reaction. We know we have two reactants and two products, so we can just write that reactant A plus B give us products C plus D. All right, and we can just work with this so it's easier to visualize things. Now, the order of a reaction. This refers to the power to which the concentration of a reactant is raised in the rate law. So for a reaction involving reactants A and B, the rate law might look something like this. The rate is equal to K, which is the rate constant, multiplied by the concentration of reactant A raised to the m power, multiplied by the concentration of reactant B raised to the n power. And M and N are the orders with respect to reactants A and B, respectively. Now, the overall order is the sum of these individual orders. We know that this reaction is a third order reaction. So in the context of this reaction, M plus N should equal 3. Now, considering this, let's tackle this next piece of information we're given. It says that doubling the concentration of the first reactant, and we'll refer to the first reactant as reactant A because it comes first in the alphabet. Now, doubling the concentration of A causes the rate to increase by a factor of 2. Now, this piece of information indicates that the reaction is first order with respect to reactant A. Why is that the case? Well, we can say that doubling reactant A, all right, is going to equal 2 to some power, M, because that's what we assigned for reactant A, and that results in an increase in the rate by a factor of 2. So what value of M would 2 raised to that value give us 2 still? That would have to be 1. So M is equal to 1. Hence, the reaction is first order with respect to reactant A. Now, we need to determine what happens to the rate when the concentration of that second reactant is halved, because this is what that problem is asking. This means that we can now begin to figure out what the order of N is. We know that M plus N equals 3. And we know now that M is equal to 1. So with these two pieces of information, we can easily figure out N, right? 1 plus N equals 3 and has to be equal to 2. Therefore, the order with respect to the second reactant must be 2. Okay, with this information, let's go ahead and rewrite the rate law a little more appropriately. The rate is going to be equal to K, the rate constant, A raised to the power 1, multiplied by the concentration of B raised to the power of 2. Now, what is our ultimate goal? To figure out what will happen to the rate of this reaction if the concentration of the second reactant, aka reactant B, is cut in half. So what we're going to do here is we are going to modify this rate law to accommodate for that change. How are we going to do this? We're going to keep reactant A fairly the same. All right, A is raised to the power of 1. Wonderful. Nothing's happening with reactant A. But what we're doing is we're going to halve the concentration of reactant B. So we're going to put 1/2 B raised to the second power. Now, from this, we can begin to simplify the expression. How do we simplify this expression? Well, this squared, this goes to this term right here, the 1/2, and it goes to the B term as well. So we can expand this expression to K multiplied by the concentration of reactant A to the power of 1 multiplied by 1/2 squared multiplied by the concentration of B squared. Now, what is this factor right here? 1/2 raised to the second power. This is equal to 1/4. So, looking at this expression, what we have here is that our rate is equal to 1/4 K multiplied by the concentration of A to the 1 power multiplied by the concentration of B to the second power. What we can determine now is that halving the concentration of the second reactant is going to decrease the rate of the reaction by a factor of 4. And that means that the correct answer here is going to be D. It will decrease by a factor of 4. Wonderful. So that is problem number 1. Let's go ahead and read problem number 2. Problem 2 says, in a certain equilibrium process, the activation energy of the forward reaction is greater than the activation energy of the reverse reaction. So we're relating delta G for the forward reaction versus delta G for the reverse reaction. This reaction is blank. Is it endothermic, exothermic, spontaneous, or non-spontaneous? So really quickly, just to redefine some important terms, activation energy, this is the minimum energy required for a chemical reaction to occur. There are different activation energies for the forward and reverse reactions. Now, Gibbs free energy, delta G specifically, this is the energy associated with a chemical reaction that can be used to do work. A negative delta G indicates a spontaneous reaction, which means it releases free energy. A positive delta G indicates a non-spontaneous reaction, which means it requires an input of free energy. Now, the information we're given here is that the activation energy of the forward reaction is greater than that of the reverse reaction. And the first thing that we should do is attempt to draw this so we can better visualize what we're dealing with. So what we're going to do is we're going to draw our axes. Our y-axis is going to be free energy, and our x-axis is going to be our reaction coordinate. Now, we're told that the forward reaction has a greater activation energy than the reverse reaction. So let's attempt to draw an energy diagram that meets that criteria. If we start our reactants over here, let's draw a big activation energy, something that looks like this. Now here, if we're moving in this forward direction, these are our reactants over here, and then over here are our products. Our activation energy is going to be the difference between this maximum energy peak all the way down to our reactants right here. So this is our activation energy for the forward reaction. Now, if we look at the reverse reaction, all right, if we look in the reverse direction right here, this would be our reactants right here for the reverse reaction. And that means to figure out the activation energy for this reverse reaction, we take the difference between this maximum energy peak all the way down to our quote-unquote new reactants. And what you notice here is that the activation energy for the reverse reaction is much smaller than the activation energy for the forward reaction. Now, if the activation energy of the forward reaction is greater than the activation energy of the reverse reaction, then the products must have higher free energy than the reactants. And we can see that if we're looking at the forward direction, and this is our reactants, and these are our products, then indeed the products have a higher free energy than the reactants. The overall energy of the system is higher at the end than it was in the beginning. And so then we need to consider, what would the delta G be then in this case? Looking at our forward reaction and comparing our reactants and products. The net free energy change is going to be positive because your Gibbs free energy for your products is higher than your reactants, and so the difference is going to give you a positive value. Hence, this is an endergonic reaction. This is a non-spontaneous reaction. And so the answer here is going to be D. Now, I also want to make note of why endothermic and exothermic here, these are not good options for this problem. Please note that while free energy does involve enthalpy, we discussed the formula for Gibbs free energy as delta G is equal to delta H minus T delta S in the lecture. While free energy does depend on enthalpy, it obviously also depends on other things like entropy. And there's just simply not enough information in this question stem to reliably determine the sign of enthalpy here in this problem. We're really focused on delta G. We're drawing the energy diagram for Gibbs free energy, hence the information that we can accurately extract from our limited information is going to have to deal with the sign of delta G, hence whether this is spontaneous or not spontaneous. And we just do not have enough information to make the jump and determine if it's also endothermic or exothermic. Hence why A and B are not good options for this problem. And of course, we looked at our reaction and were able to determine that this is non-spontaneous. So again, the answer to problem 2 is D. Let's move on to problem 3. Problem 3 asks, a reactant in a second order reaction at a certain temperature is increased by a factor of 4. By how much is the rate of the reaction altered? Now, I just want to say that I really hate the way that this problem is worded, because at a quick glance, this problem can be easily misunderstood as saying that the reaction is second order with respect to the reactant. And that is not the case. This problem is telling us that we have a second order reaction. And there is a reactant in this second order reaction that we are going to manipulate. And what is the consequence of that? And in fact, we wouldn't know, because a second order reaction can be second order with respect to one reactant, where our rate is equal to K multiplied by that one reactant, let's say A, the concentration of that reactant to the second power. Or a second order reaction can be first order with respect to two different reactants. It can be K multiplied by the concentration of A and B, both raised to one power. And indeed, we do not know which scenario we're talking about. We just have a reactant in this second order reaction, and we want to increase it by a factor of 4. All right? We cannot say how that alters the rate of the reaction, because we do not know if the reactant is second order or if it is first order, and that there is another reactant that is also first order, resulting in a second order reaction. Now, I do want to play along to this just so we can cover some basics here. If the reaction is second order with respect to the reactant, so if we're talking about this scenario right here, and then we increase the concentration of this reactant by a factor of 4, what would happen to the rate? All right, let's just play along. If that was the case, then we would want to write this as K multiplied by 4 times A squared. This squared gets distributed to both of the things inside. And so what would we have is K times 16 multiplied by the concentration of A. Here, the rate will increase by a factor of 16 if the reaction is second order with respect to the reactant. Now, what if it was first order with respect to this reactant and first order with respect to another reactant, so this scenario instead? What would happen if we increase the concentration of reactant A by a factor of 4? In this case, we can go ahead and fill this in as so. Now this one gets distributed to everything inside here, and that would give us K multiplied by 4 multiplied by the concentration of A to the power 1, B to the power 1. All right. In this case, the reaction rate would be altered and affected by a factor of 4. But again, here, we don't know which of these is the correct rate law, and thus the answer for our problem specifically is that we cannot determine the effect on the rate from this information. And that means the answer to 3 is going to be D. Wonderful. Let's move on to problem 4. Problem 4 says the concentration of all reactants in a zero-order reaction are increased twofold. What is the new rate of the reaction? So just as a reminder, in a zero-order reaction, the rate of the reaction is independent of the concentration of the reactants. This means that changes in the concentration of the reactants do not affect the rate of the reaction. Actually, the rate law for a zero-order reaction is just rate is equal to K. It's equal to the rate constant. Now, since the rate of a zero-order reaction doesn't depend on the concentration of the reactants, any changes in the concentration of the reactants is not going to affect the rate. And that means that the correct answer for 4 is going to be A. It is unchanged. Let's move on to problem 5. Problem 5 says, which of the following experimental methods should never affect the rate of the reaction? All right, so let's go through these answer choices and then work through it. So A says placing an exothermic reaction in an ice bath. B says increasing the pressure of a reactant in a closed container. C says putting the reactant into an aqueous solution, and D says removing the product of an irreversible reaction. Now, the rate of a chemical reaction, it depends on several factors, including the concentration of reactants, temperature, pressure, and the presence of a catalyst. And we discussed how these factors affect reaction rates. So, for example, for temperature, increasing temperature generally increases the reaction rate because it provides more kinetic energy to the reactants. As for pressure, for reactions involving gases, of course, increasing the pressure by decreasing the volume, that can increase the rate of the reaction by increasing the concentration of the gaseous reactants. What about concentration? That also affects. Higher concentration of reactants generally increases the reaction rate. And then also removal of products is another thing that affects the reaction rate. In an irreversible reaction, removing products can actually shift the reaction towards more product formation. This is based off of Le Chatelier's principle, and this is potentially going to affect the rate if the reaction is reversible. Now, let's go through these answer choices keeping that in mind. A says placing an exothermic reaction in an ice bath. If we place a reaction in an ice bath, all right, this is going to decrease the temperature. For an exothermic reaction, lowering the temperature will generally decrease the reaction rate because now the reactants have less kinetic energy. And you can think about this again for exothermic and endothermic reactions. For one, the heat is the product. For the other, it's the reactant. And so when you are changing the temperature, you're affecting the heat part of our reaction. And your reaction is going to attempt to compensate for that. So for an exothermic reaction, lowering the temperature will generally decrease the reaction rate. Now, for B, increasing the pressure of a reactant in a closed container. Increasing the pressure of a gaseous reactant in a closed container, that is going to increase its concentration. And this will typically increase the rate of reaction. So far, A and B both affect the rate of reaction, so they cannot be the correct answer. C says putting the reactant into an aqueous solution. This refers to changing the medium of a reaction. This is really interesting. Medium also affects the rate of the reaction. The solvent or medium in which the reaction is placed in may alter the rate of the reaction. And so this is something that we have to keep in mind. Here, we're adding the reactants into an aqueous solution. The solvent, it can influence the reaction mechanism. It might affect the solubility. It might even affect the frequency of effective collisions between reactants. And so there is the potential for that to affect the rate of the reaction. C is not the answer we're looking for. D says removing the product of an irreversible reaction. In an irreversible reaction, removing the product doesn't affect the rate of the forward reaction because that forward reaction is independent of the product concentration. Please note that this is the case for an irreversible reaction, not a reversible reaction. And so D is the only choice that answers our problem. Which of the following experimental methods should never affect the rate of the reaction? 5 is D. Next up, we have problem 6. Problem 6 asks, what would increasing the concentration of reactants accomplish in a solution containing a saturated catalyst? A says it would increase the rate constant but not the reaction rate. B says it would decrease the rate constant but increase the reaction rate. C says it would increase the rate constant and increase the reaction rate. And D says the reaction rate would be unaffected. Okay, let's start with a little bit of background knowledge. What is a catalyst? A catalyst is a substance that increases the rate of a chemical reaction without being consumed in the process. And it essentially works by providing an alternative reaction path with lower activation energy. When we talk about saturated catalyst, a catalyst is considered saturated when all of its active sites are occupied. And that means adding more reactants in this situation isn't going to increase the number of available active sites on the catalyst. Now, there's also a mention of increasing rate constant versus reaction rate, so let's briefly go over that as well. Remember, your rate constant K, this is a proportionality constant in the rate law, and it's specific to a given reaction at a particular temperature. The reaction rate, it depends on the concentrations of the reactants, and the rate constant, typically expressed in this expression, rate is equal to K multiplied by the concentration of reactant A to some power multiplied by the concentration of reactant B to some power, where M and N are the orders of the reaction with respect to each reactant. Now, with this information, let's analyze the problem. When the catalyst is saturated, all the active sites on the catalyst are already occupied. That means catalyst is operating at its maximum capacity. Increasing the concentration of reactants is not going to provide additional active sites for that reaction to occur more rapidly because the catalyst is already busy. It's already saturated. And that also means that the reaction rate is not going to increase beyond what that saturated catalyst can handle. And therefore, given that information, the reaction rate is going to remain unaffected. And that means that the correct answer for problem 6 is going to be D. Wonderful. Let's move on to problem 7. Problem 7 says a certain chemical reaction has the following rate law, where rate is equal to K, our rate constant, multiplied by the concentration of nitrogen dioxide. And here this is raised to the power of 1. So when you don't see any number explicitly written, it's going to be 1. And that's because any number raised to 1 is just that number. So sometimes it's omitted. And that's multiplied by the concentration of dibromide, also to the power 1. Which of the following statements necessarily describes the kinetics of this reaction? Now, the first statement says that the reaction is second order. Now, we can determine this because we know the order with respect to nitrogen dioxide and dibromide, so we can just sum that up to figure out the reaction order of the overall reaction. Now, the order of nitrogen dioxide is 1 and the order of dibromide is 1, and so we can sum those up, 1 plus 1. That gives us 2, which means that the reaction is second order overall, making statement 1 correct. Now, statement 2 says, the amount of nitrogen dioxide consumed is equal to the amount of dibromide consumed. This statement concerns the stoichiometry of the reaction, which is actually not directly determined by the rate law. The rate law provides information on the rate determining step and how that rate depends on the concentration of reactants, but not on the stoichiometry of the overall reaction. We would have to see a balanced chemical equation to begin to dissect this, and we don't have that information, and so we cannot confidently say that statement 2 is true or not true, and we're looking for statements that necessarily describe the kinetics of this reaction. Statement 2 is not that for us. Now, statement 3 says, the rate will not be affected by the addition of a compound other than nitrogen dioxide and dibromide. Now, this statement is incorrect because the rate can be affected by a wide variety of compounds. A catalyst, for example, could increase the rate. And so statement 3 is not true. The only correct statement is statement 1, which means that the correct answer for problem number 7 is going to be A. Great, let's do problem 8. Problem 8 says the following data shown in the table were collected for the combustion of the theoretical compound XH4. We have our reaction written here. What is the rate law? Now, our general form for our rate law, just to remind ourselves, is that rate is equal to K multiplied by the concentration of our first reactant, XH4, raised to some power, multiplied by the concentration of our second reactant, O2, raised to some power. And we're trying to figure out M and N here. So in order to do that, what we're going to do is we're going to look at our table. We're going to decide which order are we trying to figure out first. Let's say that we want to determine the order with respect to oxygen first. Okay, what two trials should we compare where the concentration of this other reactant remains the same and we're only changing the concentration of O2? That would be trials 1 and 2. Notice how the concentration of XH4 remains the same, but the initial concentration of O2 changes. That's perfect because now we can compare the direct relationship between modifying the concentration to the changes that happen to the rate approximately, and then find what that factor is and work backwards to figure out the order. So what we notice here is that going from trial 1 to 2, our concentration of oxygen gas increased by a factor of 4. Okay, so our concentration changed by a factor of 4 for oxygen. And what happened? What happened to the rate when we changed the concentration by a factor of 4? Look, the rate also increased by approximately 4. So then what number can 4 be raised to so that it also equals 4? That's going to have to be 1. So N is equal to 1, which means that the reaction is first order with respect to oxygen. Now we want to do the same thing for XH4. Which two trials maintain the same concentration for oxygen, but there is a change in concentration for XH4? That's going to be trial 2 and 3. Notice, same initial concentration for O2, but we have a change in concentration for XH4. That's perfect because we're trying to figure out the order with respect to this reactant. What's happening to the concentration going from trial 2 to trial 3? The concentration is increasing by a factor of 2. Okay, 2 raised to some m power. What's happening to the rate? Well, if we look at these numbers, we're going from approximately 50 to approximately 200. That's increasing by a factor of 4. So 2 raised to what number would give us 4? It would have to be raised to a power of 2. That means the reaction is second order with respect to XH4. Now, with this information, we can rewrite our rate law. Our rate law is going to be equal to K multiplied by the concentration of XH4 raised to the second power multiplied by the concentration of O2 raised to the power 1. This matches up with answer choice C. So the answer to problem 8 is going to be C. Wonderful. Let's move on to problem 9. Problem 9 asks, which of the following best describes the purpose of a catalyst? Before we even analyze the options, I just want to remind you that a catalyst is a substance that increases the rate of a chemical reaction without being consumed in the process. It does so by providing an alternative pathway with a lower activation energy for the reaction. Also, activation energy, this is the energy barrier that must be overcome for reactants to convert into products. Lowering the activation energy increases the rate of the reaction. Keeping those 2 points in mind, let's work through our answer choices. A says catalysts are used up in the reaction, increasing reaction efficiency. This is incorrect. Catalysts are not consumed in the reaction. They actually remain unchanged and they can be used repeatedly. So A is incorrect. B says catalysts increase the rate of reaction by lowering the activation energy. This is correct. This is actually the right answer choice. Catalysts provide an alternative reaction pathway with a lower activation energy, increasing the reaction rate. We're still going to go through C and D though. C says catalysts alter the thermodynamics of the reaction to facilitate the formation of products or reactants. This is incorrect. Catalysts do not change the thermodynamics of the reaction. They really just affect the kinetics or the rate of the reaction. So C is incorrect for that reason. D says catalysts stabilize the transition state by bringing it to a higher energy. This is also incorrect. Catalysts are going to stabilize the transition state by lowering its energy, not by bringing it to a higher energy. And so with that, the correct answer to problem 9 is going to be B. Now let's move on to problem 10. 10 says if the rate law for a reaction is the following: rate equals K multiplied by the concentration of reactant A to the 0 order, multiplied by the concentration of B to the 2nd order, multiplied by the concentration of reactant C to the 1st order. What is the overall order of the reaction? This is going to be a really simple question. The overall order of the reaction is just the sum of the exponents in the rate law. And so it can be calculated really easily as 0 plus 2 plus 1, and that gives us a total of 3. And that means that the correct answer for problem 10 is going to be C. All right, problem 11 is next, and actually for problems 11 to 13, we're going to be referencing this diagram right here. Problem 11 says, the overall reaction depicted by this energy diagram is blank. Is it endergonic because B is higher than A? Is it endergonic because C is higher than A? Is it exergonic because D is higher than E? Or is it exergonic because A is higher than E? Now, again, an energy diagram, like this one right here, displays the changes in free energy during the progression of a reaction. And it includes the reactants, products, and what you see here, some intermediate steps. Now, keep in mind the distinction between endergonic and exergonic. Endergonic reactions, these are reactions that absorb energy from the surroundings, and they're characterized by products having higher free energy than the reactants. On the other hand, exergonic reactions are reactions that release energy, and they're characterized by products having lower free energy than the reactants. The first place that we can start then is comparing the reactants, which is A, and the products, which is E. What do we notice here? What we notice is that the products have lower free energy than the reactants. And that means, based off of looking at the reactant and product, that this is an exergonic reaction because A, the reactant, has higher energy than E, the product. And that means that the correct answer here is going to be D. Now, for the other option choices here, we can notice that there's other points, B, C, and D. And B and D here, these represent transition states, and C here represents an intermediate. Now, when you're deciding the overall reaction and what it is in terms of endergonic and exergonic, you're going to be wanting to compare the reactants and the products. And that helps you begin to eliminate some of these answer choices. So in short, a system is exergonic if energy is released by the reaction. For exergonic reactions, the net energy change is negative and the free energy of the final products is lower than the free energy of the initial reactants. Point E represents the energy of the final products, and it's lower on the energy diagram than point A, which represents the initial reactants. And so that means energy must have been given off and the reaction is exergonic. Again, 11 is D. Let's now attempt problem 12. Problem 12 says, which process has the highest activation energy? A says the first step of the forward reaction. B says the first step of the reverse reaction. C says the second step of the forward reaction. And D says the second step of the reverse reaction. So let's break this down. Let's erase some of these drawings that we have on this energy diagram. And let's work through this choice by choice. So for choice A, the first step of the forward reaction, the activation energy is going to be the difference between A and B. So we would draw that out. All right, now we're going to keep this pretty simple. We're just going to draw it out first and see if we can distinguish clearly which of these answer choices is right. B says the first step of the reverse reaction. So going this way, that's going to be the first step of the reverse reaction. So the difference between E and D. So that's that activation energy for B. And let's label this. This is for answer choice A. This is for answer choice B. All right, answer choice C says the second step of the forward reaction. So now we're looking again at our forward reaction. The second step is going to be the activation energy difference between C and D. So that's going to be this point right here and this point right here. So that is for answer choice C. So this is A, B, and C. And then D is the second step of the reverse reaction. So now we're looking in the reverse direction, and that is also going to be the activation energy difference between C and B. So this is both the answer choice for C and D. Now, just looking at our drawing of our relative bars for activation energy, B is the largest. This is going to be the greatest activation energy, the largest activation energy. So it's going to be that first step of the reverse reaction, which means that the correct answer for 12 is B. So just to summarize, again, the activation energy of a reaction, that's going to be represented by the distance on the y-axis from the energy of the reactants to the peak energy prior to formation of products. That activation energy of the first step of the forward reaction, for example, that was equal to the distance along the y-axis from point A to B. And we went ahead and we drew this relative bar for each of our options here. And we saw that the largest energy increase on this graph occurs during the progress from point E to point D. And that represents that first step of the reverse reaction, which is why 12 is B. Beautiful. Now we can move on to problem 13, which is the last problem that's going to reference this energy diagram. Problem 13 says point C in this reaction profile refers to the blank. Is it reactants, products, transition state, or intermediates? Now, your reactants for this forward reaction is going to be A, and your products for the forward reaction are going to be E. Now, in the reverse direction, that's going to switch, right? E is going to be your reactants. A is going to be your products. What's not going to change is what we call B and D and what we call C. B and D represent the transition states for this reaction. And a transition state is a high energy state through which the reactants must pass to form the product. And so it represents the peak of the energy barrier. C here, which is like this little valley, this is a intermediate. This is a species formed during the reaction that is not the final product. It is usually at a local minimum between two transition states. And that is what describes C. It is an intermediate. That means the correct answer for 13 is going to be D. Wonderful. Now we can move on to problem 14. Problem 14 says that the following system obeys second order kinetics. And we're given two reactions, one that is slow, one that is fast. So we're given this reaction mechanism. What is the rate law for this reaction? Now, the rate law, we said, is based on the slow step. It's based on that slow rate determining step. So let's go ahead and begin to focus on the slow step. What do we have here? We have one reactant. And so that means if we were going to set up a rate law for this slow reaction, we would write that rate is equal to K multiplied by the concentration of nitrogen dioxide raised to some power. Raised to some power. There's only one reactant, and we know that the slow step is what our rate law is based on. We're also told that the system obeys second order kinetics. Since there's only one reactant, then the order of this has to be 2. And so our rate law is going to be equal to K multiplied by the concentration of nitrogen dioxide raised to the power of 2. And so in short, since this is the slow step, it determines the overall rate of the reaction. There is only one reactant in the rate determining slow step. And since we know that the system obeys second order kinetics, that means that the order of the reactant is going to be second order. And the final answer is going to be answer choice D. There we have it. So this question, it could be tricky if you forget the fact that the rate law is based on the slow rate determining step. That's the key to figuring out this problem. And then it becomes easy because you only have one reactant. And so the rate, remember, is always related to the concentration of the reactants in that rate determining step, not the overall reaction. So NO2, nitrogen dioxide, is the only compound that should be included in the correct answer. And the concentration of nitrogen dioxide is squared in the rate law because the question tells us the system obeys second order kinetics. And I know I repeated that in maybe 3 different ways, but I hope that at least one of them resonated with you. So the answer to problem 14 is D. And now we can move on to our last and final question, problem 15. Problem 15 says the potential energy diagram shown represents 4 different reactions, A, B, C, and D. Assuming identical conditions, which of the reactions displayed on the energy diagram proceeds the fastest? The key to answering this problem is just remembering one simple fact. The lower the activation energy, the faster the reaction proceeds under identical conditions. This activation energy is going to be the difference between your reactants and your peak energy barrier. All right, the peak of the energy barrier, the transition state. Now, looking at these answer choices, it is pretty clear that D is going to have the smallest activation energy. Look at that. Here's that peak, and here's where the reactants are, very small. And we can go ahead and draw the relative scales for all of these. So this is for A. Oops, that's too long. This is where A is. Here's where B is. That's going to be the red one. And here's where C is. And so just looking at these bars, it's really clear that for energy diagram D here, it has the lowest activation energy required. And so this reaction is going to proceed faster under identical conditions. And the correct answer for 15 is D. And with that, we've completed this practice problem set. I hope that this was helpful. Please let me know if you have any questions, comments, concerns. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.